First of all, if you have question about AVL tree, it's the time. Please ask your questions about AVL tree. Red-black tree is very similar to AVL tree. We are going to talk about a red-black tree today. Remember, red-black tree is used to implement tree tree set and tree map structures. And so today we are gonna talk about red-black trees. If you have a question about AVL tree that we have discussed last time, you can ask right now, or I'm gonna start talking about red-black trees. Okay, I think you don't have any question. So, red-black trees is another balanced binary search tree we are going to talk about. It is first developed as a special case of B-tree. B-tree is another balanced search tree that we are going to talk about later on today or next week. It's a special case of B-tree, and it is improved by Guibas and Sedgwick later on, and they introduced this red and black color convention. In red-black tree, we have several invariants, several conditions that tree needs to be satisfied. First of all, each node is colored by red or black. As you see here, each node is either red or black. It's a binary search tree all in all. As you see, everything less than 11 are on the left and greater than 11 are on the right. And it is like that for all the other nodes as well. It's a binary search tree. But the nodes are colored either with red or black. Another one is root is always black. As you see here, root is black. We cannot make root to be red. If root is red, we change it to be black. Later on, we are gonna see how we are gonna make color changes during insertion and deletion. Another condition, a red node always has a black child. As you see, this red node has black children. We may have a red node here. It should have black children. And we have this red node, which doesn't have any child. We can consider as having null red black children. So null reference can be considered as black node. In this case, we have black nodes here which are null. Let's say we put it like this probably. So each red node has two black children. Either this child and any child is null reference or a real node, okay? And then the last condition makes our tree to be balanced, the number of black nodes is same for all paths from root to leaf. Okay. For example, here we have two black nodes. Here we have two black nodes. Here we have two black nodes, and here again we have two black nodes. We cannot have more than two black nodes in this tree. Of course, we may add new black nodes on the paths, but again, the number of black nodes for all the paths should be same. That makes the tree balanced. How? We do not count the red nodes, but when you see the black nodes are balanced. And when you consider only black nodes, the height is determined by counting only black nodes. So the height is true in this case. And when you consider the height of the left subtree and right subtree, these trees, if you consider only the black nodes, the height is same. Both left subtree has height 1 and right subtree has height 1. So it is a balanced tree with no height difference between left subtree and right subtree. It is like that for all the nodes, even for the red nodes. For example, for this red node, left subtree and right subtree has same height. Both are 1. You count only the black nodes, as I said. So red-black tree is balanced, means the left and right subtrees have the same height, considering only black nodes. Okay. Then you have to search this red-black tree. It is a binary search tree, so you can search with a regular binary search tree find operation, right? You start with the root and compare. If it is smaller, continue with the left subtree. If it is larger, continue with the right subtree, right? If it is equal to, of course, you have to stop search operation and give the result. If the tree is null, you have to stop and say the value is not available. So the search operation is same as the regular binary search tree. It was like that for the AVL tree as well. AVL trees are also regular binary search trees, but there is a special balance criteria in AVL tree of height differences at most 1. Here the special criteria is height difference is 0, but only counting the black nodes. Okay. So for insert operation, first of all, we have to remember in both binary search tree and AVL tree, we perform something like search operation. And then we make sure that the item is not available. For example, if we have to insert 9, 9 is greater than 11, so we insert on the left subtree. It is greater than 2, so we have to insert on the right subtree. greater than 7, so we have to insert on the right subtree. Greater than 8, we have to insert on the right subtree, which is empty. There we understood that the element 9 is not in the tree, and this is the insertion position. We have to insert 9 over here, right? As in the binary search tree. But how we are going to insert this 9 and what would be the color of 9? We should be careful on that. If we color 9 to be red, 2 red nodes will be one after the other. If we color 9 to be black, this path will have 3 blacks, and this path will have 2 blacks. It will violate the fourth condition. So whatever the color we give to this node, the invariance will not be satisfied. So we have to be careful about it. For example, if we insert 15, we can insert to the right of 11, right of 14, and 15 is here. If we color this node to be red, then all the invariants are satisfied, right? That's why we insert the nodes at the leaf, new nodes, new elements at the leaf. Then we make sure that the item is not in the tree. We insert over there and give that node color red. If the parent is red, as in here, black as in here, if the parent is black, we don't need to do anything further since the invariants are all satisfied. But if the parent is red, as in here, this condition is violated. So condition invariant 3 is violated. So we have to perform some operations to correct that problem. Okay, so if the parent is black, we are done. Otherwise, we need to rearrange some things to correct the situation. There we have 3 cases. When you insert a new node, which is colored to be red, and if the parent is red, we have to do something, and we have 3 cases over there. First case is when you insert 35. We know that 35 is red. We know that 30, which is the parent of 35, is red, since otherwise we do not need to do anything. And case 1 says that the sibling of 30, sibling of the parent, is also red. So the case is, if a parent is red, if the parent is not red, if it is black, we do not need to do anything. If the parent is red and its sibling is also red. If both these are red, we can convert them to black. But if we convert them to black, consider this in another tree, in a tree, as a subtree. If we convert this to be black, then some of the paths, these paths will have one more black than this one. That's why we convert this black to be red as well. So we convert these two siblings to be black, and its parent, grandparent of 35 to be red. Now, if this is a big part of a big tree, for example, like this becomes red. It used to be black. Depending on the parent, the problem would be shift to upper levels. For example, if the parent is red as well, it can be red, then we have a situation here. We had a situation here beforehand. Now we may have a situation here. Of course, the parent would be black, and we can stop over there. Or if we have this to be red, we have to continue fixing. But if this is the whole tree, then this is the root. If the root becomes red, we have to correct it. We have to convert it to black for the second condition. Okay, the root can be changed to black, and when we change this to be black, still fourth invariant is satisfied, as you see. Both paths from root to leaves are having two black nodes. Okay, so if if the parent of a node, new node, is red and its sibling is red, what we do is we convert the parent and sibling to be black and their parents to be red. This is what we do to fix the problem over there, but in this case, we may have shift the problem to upper levels. We continue fixing until the root node probably. So if we have a large tree, we may have a problem here. We fix it, we shift to over there, fix it, shift to over there, fix it, shift, and when we come to root becomes red, and we can easily convert it to be black. If the same problem again and again through the two different levels, to upper levels of the tree. Okay, remember in AVL tree last time, when we fix a problem somewhere after insertion or deletion, the problem doesn't propagate, never propagates. When we fix it, it is fixed. But here in red-black tree, the problem would propagate to upper levels. Okay? Okay. The first case is this one, when the parent and its sibling are red, What would be the next case? Next case is when the parent do not have any sibling or actually a we can consider this sibling to be black as well if it is part of a bigger tree. If there are lots of nodes here, since this red condition can happen since red propagates up to upper levels, then we have this kind of situation, and the sibling is black, not red, black. If the sibling is black, or if we don't have any sibling of the node, we have case 2, and as you see, we have right case. Similar case could be left case, as in AVL tree. Since case 3 will be this case. Again, the parent is red, of course, but sibling is not available or black. But in this case, right, left case. And there is a symmetric one, left, right case, right? This is right, left. Left, right is symmetric of this. We are going to consider later on. Okay, this is case 1, right? We have corrected it. This is case 2. In case 2, the parent is red, but it doesn't have any sibling or black sibling. In that case, we cannot change this node to be black, parent to be black. We cannot change parent to be black, since we can violate this condition 4. Right? So what we do is we make this change. The parent is black and grandparent is red, but we do not stop there, since this condition is violated, at least here. We have to continue. How? As you see, there is one black node on the right on this path, but no black node on this path. So the fourth condition is violated. So we have to correct it. We correct by left rotation around 20 and make this one. Of course, while making this rotation, if there are available trees here, these trees could be distributed correctly. If this is A, this is B, this is C, this is D. CD will be stay left and right subtrees of 35. A will stay as a left subtree of 20, but B will not be left subtree of 30, but right subtree of 20, right? So A should still here, and B comes to this position and C, D are still over here, right? So we perform a right rotation. As you see, before insertion, or before we have this, when we have this violation of third condition, we have 2 or 3 pads. All of them has one black node. And after fix, again, we have several pads, and all of them has one black node over here, right? Of course, we may have several black nodes over here, but these black nodes should be same anyway, right? The height of these trees should be same in terms of the number of black nodes. So this heights are same before when we have this problem. When we have this problem, we may have some trees here. All of them should have same black height, right? And after this change, all of them have same black heights again. So all of the invariants are satisfied. Of course, after insertion, we cannot have these and this probably, but as I said, after making operations, this red situation propagates up. At that time, we may have these subtrees, right? So second case is when the parent is red and right sibling, the sibling is black or none, but it is right situation. The third condition is, again, parent is red. The other sibling of parent is black or none, but it is right left case. In this case, performing the same operation as in case 2 doesn't solve the problem. What we do in case 2, remember, first we make the parent to be black and grandparent to be red, like this, and perform a rotation operation. And you perform rotation operation, we still have 2 red nodes, but this time left-right case. So it is a symmetric of the symmetric case 3, so it is not solved at all. So we have to perform some other thing. We do not perform a rotation over here directly, but first we perform a rotation over 30. As in AVL tree, 2 rotations will be done. Then we perform this rotation, the tree becomes like this, and it is exactly similar to right case, right? And it can be correct by rotation over 20. We perform color change right now and perform rotation. Again, after rotation, the tree is balanced. So we are done. Okay. For example, if we have to insert a node over here, 4, this violates the third condition. red registration, and left case. What we do, and the sibling is red as well, as you see. This is case 1. We make parent and sibling to be black and grandparent to be red. Now the problem is shifted over here, right? And we have case where the parent is red, grandparent is black, parent sibling is black as well. Parent sibling is black. So this is case 3, left-right case, right? So we perform a rotation over here first, O2, make this one, and make color change between 11 and 7, and perform a right rotation over here to get this one. Now the tree is balanced. So as you see here, when we perform case 1, the problem shifted up, and this was, if this was part of bigger tree, after case 3, the problem is solved, and as you see, before doing anything, all the paths here has true black. After the operation, everything has true black, and here actually all have true blacks. So the problem solved and cannot propagate further. The problem can propagate further in case 1, but in case 2 or 3, the problem doesn't. Okay. So this is the whole cases. As you remember, we have talked about 3 cases that can happen. Remember here, let me go back. Yes, we talk about 3 cases. When we insert a new node and color it to be red, we have 3 cases. One of the cases when we insert here as a red, and the parent and sibling are red. The second case is we again insert over here, parent is red, but the sibling is black. Third case is we do not insert here, but here, again, parent is red and grandparent is black or not available. This case, when we insert here, parent is red and grandparent is black, can be solved as case 1 as well. We color both parent and grandparent, parent and sibling to be black and grandparent to be red. So this is also right left and case 1. Also inserting over here as red is case 1. Inserting over here as red is case 1. All these are case 1 and corrected by this operation. Change sibling and parent to be black and grandparent to be red. These are all case 1. And having inserted here is case 2. Having inserted here is case 3. Since the sibling is not available or sibling is black. Okay, we have 3 cases. Now we are gonna have this example. We are gonna insert these words of the sentence one by one in an empty tree. First, we insert the, and this is the only element in the tree, so we do not need to do anything. It is balanced, and it is inserted to be red, and it is converted to black right away, since it is the root node. Root should always to be black. When we insert quick, it is on the right of 3, and it is inserted as red, and still there is no violation, so the insertion is completed. Then we have to insert brown. Brown is on the right of 3 and left of quick. Why is it right of 3? Since T here is capital. Capital letters are before the small letters, non-capital letters in ASCII table. Okay, we insert here, and here, as you see, we have red situation, and as you see, it is left-right case. It is case 3. So first we have to perform a rotation over quick. Now it looks like case 2, and we change the colors of these true nodes and make a right rotation over the. And this is the what we have after the rotation. Now it is perfectly fine red-black tree. We continue with fox. Again, here we have a situation, red case. And as you see, it is right-left situation again. Excuse me. It's right-left situation, but right now the parent has sibling and it is red. So it is case 1. So how we fix it? Make these to be black and brown to be red. But brown is the root node, so we cannot violate this condition. Make brown to be black as well. And we are done. And we insert jumps. Parent doesn't have a sibling and left-right situation. It is case 3. So we perform a left rotation on fox, then change the colors of quick and jumps, and make a right rotation over quick. And we are done. Okay. Then we insert over. As you see, over is red, parent is red, parent sibling is red as well. So this is case 1, and it will propagate upward. We are gonna see that. Case 1. So we make these true to be black and jumps to be red. Okay. And now jumps becomes red, we have to check its parent. Its parent is black, so the situation will not propagate. There is no further operations are required since we solved the situation over there. Then we insert V. There is nothing to do since the parent is black. And we insert lazy. Parent is red. The sibling of the parent is red. So we have case 2, case 1, excuse me. So we have to color these two to be black and quick to be red. Now we have a situation here as well. As you see, red situation. Parent is red and sibling is black, and it is right situation. So it is case 2. We have a case 2. We can correct this case 2 by left rotation over brown. So then we first we have to change the colors of brown and jumps. Jumps becomes black and it will become the parent. Brown becomes red and left child of jumps, quick will be quick is red and it is right child of jumps, and it is done. Case 2 is done and everything is fine. We can continue with the dog. When we insert dog as red, its parent is black, so we do not need to do anything. This is all. So we have inserted everything, and as you see, the tree is balanced. Number of black nodes on all over the all root to leaf paths are 2, so we are okay. And you can also see the black height for the left and right subtrees are 1 as well for jumps. Okay, it's balanced. How we are going to implement it? Similar to AVL tree, we have to extend node structure with red-black node. In red-black node, we need one more data field to check whether to say that the node is red or not. Remember, in AVL3 we put a data field to signify whether the node is balanced or not, or left heavy, right heavy, or balanced actually. Also, we have to extend binary search tree with rotations to get red-black tree. Of course, we have to override these two operations, add and delete of binary search tree to perform these operations faster. Okay. The operations are in this page 497 in our book. I'm not going to go into details of these operations. Please look at these operations, the algorithm and the code, everything. Carefully review the code and make sure that the operations are implemented perfectly. I'm not going to go over this code with you. It is your self-study assignment. In there, in remove, if we delete a leaf, it has no child. So we can delete it if it is red without any harm. But if we have to delete something else, we have to find it is in order predecessor and replace the node with that in order predecessor as in binary search tree, remember. If the node has only one child, again, we can easily remove the node as in binary search tree. But when the node which is leave for one child or in order predecessor is we are removing that node. If that node is red, we are done. We do not need to do anything. We do not harm any condition. But if we remove a black node, then we have to be careful. If that node has a red child, we can convert that children to be black and we are done. But if there is no black child, then a black leaf or a black node with black child. And if we remove that node, black height becomes unbalanced. So we start to violate condition 4. And we have to fix that condition. There are several cases, again, to fix the problem, but can be done with some rotations, etc. Color changes and rotations are performed and we can solve the problem. The implementation of removal is left as programming exercise to you, so you can try it by yourself. Okay, whatever the red-black tree's height, it is less than this big, since each node we are talking about black height and the total height is twice as big as black height. So it is twice as big as log n. Okay, true log n is logarithmic in big O notation or theta notation. So the both search, insertion, and deletion operations will be logarithmic time. And actually, experimental studies show that when you perform these operations, the number of comparisons are limited to this big, not twice, only 1.002 times log n. So the performance is a lot better than this worst case in experimental studies. So red-black trees and AVL trees are not complete binary trees. but their performance is similar to complete binary trees or perfect binary trees. And they are regular binary search trees, right? Binary search trees with some modification during insertion and deletion, right? Okay, as you remember, tree map and tree set are implemented using red black tree. Okay, I'm gonna stop here for the break. After the break, I can take your questions about red black tree, and we are gonna continue with two tree trees, which is another balanced search tree. It's not binary tree as we are gonna see. It is balanced search tree only.